Alright, so we just finished figuring out how to solve linear homogeneous equations. These are equations where the right-hand side is 0. And we've discussed the general solution of a linear equation as having two parts. The first part is a general solution of that homogeneous equation, which we just learned how to do using characteristic equations, just basic algebra. That's what it all is. Now we want to add to that general solution of the homogeneous equation one particular solution of our general equation, L of y equals some function phi of x. So once we add those two together, that forms the general solution of this equation. Because in a sense, when we find a solution, a particular solution to this equation, and we add the solution to the homogeneous equation, we're in some sense just adding 0. We're not adding 0, but when we plug it into the linear differential operator L, that part will vanish. So in order to find these particular solutions, we're going to talk about one method called the method of undetermined coefficients. And it really has to do with linear combinations and linear independence, and using ideas from there to basically make educated guess at what this particular solution should look like. And then once you have a guess at what it looks like, you can plug it into the equation, and that'll actually give you a system of equations which will allow you to determine exactly what it is. So we make an educated guess of a general form of our particular solution, and it's going to have some coefficients, the undetermined coefficients, in it. And then when we plug it into our linear differential operator and set it equal to phi of x, we're basically going to be comparing two functions. One is determined, it's phi of x, we know what it is, and the other one we don't know, it has some constant coefficients in it. And by comparing those two functions and equating them, we're going to use linear independence of both sides of the equation to basically pair up coefficients of different functions and say that they have to be equal using the linear independence of those functions. So it'll give us a system of equations. So the general idea is we want to identify this phi of x that we're given as a linear combination of some general set of linearly independent functions. The sum of the coefficients we will actually be 0 to represent phi of x. But we want that list of linearly independent functions to be somewhat big enough so that when I plug any kind of combination like that into L, it will give me another combination of the same kind of function. So the basic three examples are, we're going to talk about polynomial functions, exponential functions, and then the trig functions with sines and cosines. These will make up the kind of basic idea of how this method works. So, for example, just think of, we have a solution. We're looking for a solution to this equation. And suppose that the solution is actually some polynomial function, which is just some numbers times different powers of x. That's all polynomial is. And now imagine if you take such a function and you compute its derivative. Well, what do you get? You're going to get another polynomial function, but it's going to have the highest power is going to be one less than this one. And if I take another derivative, it'll still be a polynomial function, but it'll have a highest power that's even smaller. This is just the power rule. So when I compute a bunch of derivatives of such a function, and then I add those functions together as a linear combination, which is what L is going to do, I'll just group the like terms together, and I'll still have another polynomial function. So essentially, if you plug a polynomial into a linear differential operator with constant coefficients, the output function is also going to be a polynomial function. So this is what we mean by preserving the type of function through the operation L. Another type is when we look at exponential functions. If we have some linear combination of different exponential functions, and I'm saying these are different because these numbers b1, b2, up to b sub m are making them different in the sense that each of these functions is linearly independent, because the values of the b1, b2, and so on are all different numbers. So this is what you may have seen as saying they have different base. These exponential functions have a different base e to the b1, e to the b2, and so on. So if we have a function like this, and again, what happens if we differentiate this function? Well, each term is going to be basically the same kind of term. It's going to be the same kind of exponential, but it's going to be a different constant in front by the chain rule. So if we take a whole bunch of derivatives of some function like this, it's still going to look like this general format. It'll still be of this general linear combination form. So this kind of linear combination is going to be preserved by a linear differential operator with constant coefficients. It's just going to change the coefficients, but not the base functions, not the exponential functions. And in the last case, we could have a trig function like a sine or cosine. We could just have one of them, or we could have some combination of two of them like we have here at the bottom. So if you have y as some function like this, imagine what happens when you differentiate y. You're going to have to use the chain rule. So the constants in front of the sine and cosine are going to change. The cosine is going to change to a minus sign, and the sine is going to change to a positive cosine. So in the end, the derivative of this function y here at the bottom is going to be of the same form. It's going to be some constant times the sine of bx plus some constant times the cosine of bx. And every time I differentiate this kind of function, it'll still have that general linear combination form. So linear combinations of a sine and cosine, as long as they have the same number b inside, the same frequency, then any function like this will have the same form as the function we get after we plug it into our linear differential operator L. So these are the three basic types of things we generally run into. And we want to kind of talk about next is how do we use this idea, this preservation idea, this idea that L takes a certain kind of linear combination to the same kind of linear combination. We're going to use that idea to basically take an educated guess at a particular solution of our equation. But we're not going to be able to just guess the exact solution. We just want to guess a general form, like one of these forms. And then we're going to have coefficients that we don't really know. And then when we plug it into the differential operator L, and then write that as a new linear combination of the same functions, we can compare it to whatever phi of x is, and that'll tell us what those constants are going to have to be.